Section 1 Introduction. We're here to introduce our research on autoregressive text-to-image models, which have made significant progress in generating detailed images, similar to the achievements of diffusion models. These models are architecturally similar to large language models, LLMs, but they are specifically trained for paired image-text data. LLMs, however, are only capable of producing text-based output, which means they lack the ability to generate multiple types of output, despite their proficiency in text-based tasks. Recently, there's been a surge in interest in multimodal large models, which aim to combine the strengths of vision and language models. Despite some progress, these models are still primarily generating one type of output, limiting their expressiveness. Our study aims to overcome this limitation by developing a multimodal model that can generate both text and image outputs. To achieve this, we've conducted an extensive empirical investigation into the combination of two specialized autoregressive, decoder-only, large transformer models, each designed for unique tasks, one for text-to-image and a text-only model. We've developed a set of methods under the Joint Autoregressive Mixture (JAM) framework. This framework leverages the architectural compatibility of autoregressive text-to-image models with LLMs, enabling us to deeply fuse and jointly train the models in ways that wouldn't otherwise be possible. Our solution is modular and data efficient, allowing for deep, quick, and effective integration of continually evolving large models, using less than 1% of the original pre-training data for both parent models. Our contributions are twofold. First, we demonstrate the feasibility of merging autoregressive text-to-image models with LLMs into a unified architecture that retains the strengths of each while revealing new capabilities. Second, we present innovative strategies for multimodal instruction tuning, using text-based instructions and a custom-curated dataset designed specifically for image generation. The result is a first-of-its-kind large multimodal model that can coherently generate long-form content with interleaved text and images. To create a unified model that excels at vision-language generative tasks, we propose to combine two autoregressive decoder-only architectures. Our primary image-text model is CM3 Leon, trained on 2.4 trillion image text caption tokens. In contrast, our LLM has been trained on 1.4 trillion text tokens. Both models have 7 billion parameters. Our methodology develops in two stages. First, we combine and align the models. Second, we explore new directions for instruction tuning focused on interleaved image text generation. We combine the two pre-trained models into a single, cohesive structure in our proposed framework. This composite model is fine-tuned using a hybrid dataset comprising both text-only and image-text samples. The central motivation behind this approach is to seamlessly merge the capabilities of two pre-trained models, capitalizing on the unique strengths of each. The concept of model merging has been previously used to combine models that share identical optimization trajectories, or models that are trained on identical datasets but have independent optimizations. A consistent approach across these studies is to combine models without any training. Our approach diverges from this convention. We view the merged model as a powerful initialization for subsequent training on mixed-modal data. The weights of the averaged model are defined as the average of the weights of the LLM and the text-to-image model. In this study, we explore weights merging specifically to multimodal decoder-only large transformer models, and notably, on an unprecedented scale, involving models trained on trillions of tokens from diverse datasets. We refer to our average model as JAM uniform. Our second approach employs the pre-trained weights to initialize a wider architecture. Our new model has hidden dimensions of 8,192, which is double the size of the two original models. We keep the same number of layers of the original architectures. The resulting architecture has 26 billion parameters, initialized starting from the pre-trained weights of our backbones. The token embedding input-output projections and the learned positional embeddings of the two initial models are concatenated on the hidden dimension. The attention weights are initialized as a matrix with the weights for the query projection of a generic attention layer from both models. All the other weights are initialized following the same logic. We also experiment with slight variations of the approach, using the average to initialize half of the new parameters. We name the resulting model JAM width. Section summary. In this section, the authors introduce a multimodal model that combines autoregressive text-to-image models with large language models, LLMs, to generate integrated text and image outputs. They propose a Joint Autoregressive Mixture (JAM) framework that allows for deep model fusion and joint training. The authors present two methods for model merging: JAM Uniform, which averages the weights of the two models, and JAM Width, which initializes a wider architecture by concatenating the pre-trained weights. These methods enable the generation of long-form content with interleaved text and images. Section 2.1.3 Cross-Model Fusion. In this section, we'll discuss our approach to cross-model fusion. We suggest incorporating cross-attention layers between the base models to enable smooth information exchange while maintaining the knowledge of the original models. We're working with two decoder-only transformers models, which we'll call T_LLM and T_IMG. We've introduced a two-way cross-attention mechanism that allows the layers of one model to pay attention to the output of the corresponding layer in the other model. This method promotes a gradual exchange of information at various representation levels. Let's consider a specific layer, which we'll call layer L. The models generate sequences of hidden states, H_LLM, L for T_LLM, and H_IMG, L for T_LLM, which are the outputs from layer L. The output of the cross-attention mechanism, H_cross, L, from T_IMG to T_LLM for a given layer is calculated as follows. First, we calculate Q_cross, L, K_cross, L, and V_cross, L. These are obtained by multiplying the weights W_Q, L, W_K, L, and W_versus L with the hidden states H_LLM, L1, and H_IMG, L1. Then, we calculate H_cross, L using the softmax function applied to the product of Q_cross, L and the transpose of K_cross, L, divided by the square root of D_K. Here, W_Q, W_K, and W_versus represent the weights of the query, key, and value projections of the newly added cross-attention layers. We apply a similar process for the reverse direction from T_LLM to T_IMG. We use a shared input-output projection layer, initializing the weights of the text tokens from the LLM input embedding and the weights of the image tokens from the image text model. We add a new linear projection layer that takes the combined output embeddings of the two models as input. We refer to the model resulting from this approach as JAM cross. Next, we'll discuss multimodal conversational instruct tuning. Supervised fine-tuning is a crucial tool to enhance the capabilities of large pre-trained models. Recently, instruct tuning has been extended to a multimodal setting. However, all the existing methods are focused on visual understanding abilities. In this work, we study instruction tuning tailored to interleaved image text generation. We collect a small and curated mixed-modal dataset to teach our JAM model to support textual explanations with coherent images. In the first stage, the model has been trained on image text captions and text-only data. During this phase, we train on interleaved image text data. We demonstrate that the model can quickly learn the style of images and text from a small curated dataset. Our results suggest that the superficial alignment hypothesis introduced in Lima holds not only for learning the text style but also for images. In our experiments, we consider two slightly different instruction tuning settings. We introduce a small portion of the image text Shutterstock data with retrieval augmentation, and we find this approach beneficial to preserve the generated image quality when generating with retrieval augmentation. We train using a standard supervised procedure without leveraging any reinforcement learning or human preference strategy. In this instruction tuning phase, we leverage interleaved image text data in contrast to previous methods that rely only on image text caption and no instruction tuning. Our experimental results confirm the benefits of training with interleaved image text data. In our experiments, we use the VQVAE tokenizer for images. The image resolution is set to 256 by 256. Each image is represented by 1024 tokens, and the vocabulary has a size of 8,192. Our text tokenizer is the same that have been used to train the two parent models, trained over the data for text. We introduce the additional less than break greater than token used by CM3 Leon to identify a modality break. We adopt CM3 Leon as the image-text autoregressive backbone. The model has a standard decoder-only architecture with some peculiarities: no bias terms, dropout, and learnable parameters for layer norms. It has been trained on 2.4T image text tokens and uses a sequence length 4096. As an LLM backbone, we select a model with the same architecture as CM3 Leon. Trained in this allows us to experiment with a broader range of approaches, such as weight averaging and width concatenation. The model is trained on 1.4T text data with a 2048 context length, and we further fine-tuned it with a 4096 context length using only 30B text tokens. Section Summary. The proposed approach introduces cross-attention layers between two decoder-only transformer models, allowing for the exchange of information at different representation levels. The model configuration, referred to as jam cross, utilizes a shared input-output projection layer and a new linear projection layer that takes the concatenation of the two models' output embeddings as input. In the multimodal conversational instruct tuning phase, the model is trained on interleaved image text data, demonstrating the benefits of training with this type of data compared to previous methods that rely only on image text captions. Section Objective. In our experiments, we use the CM3 objective, which was introduced in previous research. This objective takes the original sequence and either uses it as is or transforms it by masking certain parts and moving them to the end. The model is then optimized to minimize the standard autoregressive loss, which is the negative logarithm of the probability of the input sequence. This objective allows for optional bidirectional processing and enhances the model's flexibility, making it suitable for both infilling and standard autoregressive generation. We ensure that the objective does not mask across the modality tokens. For our training procedure, we use multimodal retrieval augmentation, which was introduced in previous research. We take advantage of modifications to our text-to-image backbone that were introduced in other studies. The retrieval process uses a dense retriever and a specifically chosen retrieval strategy. The retriever takes an input query and returns a relevance score for each candidate document in our memory bank. Each multimodal document is divided into text and images and fed into the corresponding modality-specific VITB32 clip encoder. The two embeddings are then averaged to form the vector representation of the documents. We then use maximum inner product search over the memory bank to get a list of candidates. When sampling retrieved documents, we prioritize diversity by skipping candidates with a score less than or equal to 0.9. We apply query dropout to regularize the training, dropping 20% of tokens from the input sequence. During the continued pre-training, we train for approximately 50 billion multimodal tokens. Our initial learning rate is 0.00003, and we use 500 warm-up steps. We set our optimal batch size to 8 million tokens, a hyperparameter borrowed from the mixed-modal scaling laws introduced in previous research. The total number of training steps is 5,960. This training procedure takes about 1 day on two 56 80GB A100s for all models. We select the last checkpoint for all the different jam models, which is always the one with the lowest average validation perplexity. All our training procedures are implemented using Metaseq. Our instruct tuning training procedure is data efficient. We train with our instruction tuning mixed corpora. The initial learning rate is set to 0.00001, and we use 300 warm-up steps and a batch size of 1 million. The instruction tuning procedure takes less than 2 hours on 64 80GB A100s. We train for 15 epochs over our mixture of datasets and manually select the best checkpoint corresponding to the 9th epoch. We observe that the validation perplexity doesn't correlate with the quality of the responses. We implement a mixed-modal decoding strategy for our interleaved generation. The model starts generating text tokens until a modality token is detected, then an image is sampled, and the generation continues until an end-of-sentence token is sampled. We use temperature sampling, a common technique used in autoregressive models, to control the randomness of the prediction by modifying the softmax temperature. We pair this technique with top sampling, which involves sampling from the top-ranked tokens with a cumulative probability exceeding a predefined threshold. We also use classifier-free guidance for sampling images. This technique allows us to condition the sampling procedure, blending the logits from an unconditional sample with the logits from a conditional sample. The procedure is mathematically described as the logits from the classifier-free guidance being equal to the logits from the unconditional sample plus a scaling factor times the difference between the logits from the conditional sample and the logits from the unconditional sample. Thanks to the CM3 objective, our training procedure allows our models to sample with classifier-free guidance without further fine-tuning. We complement this technique to boost the generation quality. Our samples are generated using a temperature value of 1. The top threshold is set between 0.8 and 1, and we use classifier-free guidance with values 3.5 and 4. Unlike other approaches, we don't use the computationally expensive clip re-ranking or contrastive decoding. We randomly sample a subset of 30 billion tokens from CM3 Leon pre-training data. The data consists of legally acquired image caption pairs from Shutterstock, a commercial online platform offering images with ownership attribution and clear licensing terms. Section Summary. The objective of our experiments is to optimize the CM3 objective, which accepts the original sequence or transforms it into an infilling instance by masking specific spans and relocating them to the end. We employ multimodal retrieval augmentation using a dense retriever and a specific retrieval strategy, and during training, we prioritize the diversity of the sampled documents. We use a mixed-modal decoding strategy for interleave generation, employing temperature sampling and top sampling, as well as classifier-free guidance for sampling images. Our training procedure allows for CFG sampling without further fine-tuning, and we use a subset of 30B tokens from CM3 Leon pre-training data sourced from Shutterstock. Section: Text Corpora. We've used a vast collection of text tokens, about 30 billion in total, gathered from various public sources. This is the same data used to train other popular open-source language learning models. The sources include English Common Crawl, C4, Wikipedia, Books 3 from the Pile, and Archive. We also used the 1K dataset from Lima, which contains a variety of carefully selected prompts and responses. Additionally, we collected a dataset of image text pairs from 3,000 articles on WikiHow, an online wiki that typically provides suitable images for each article. We chose articles from different categories to ensure variety and used the community ratings on the platform to select high-quality articles with a score of over 90 out of 100. We used the title of each article as a prompt and limited the number of images to 3 per sample to fit our 4096 context length. In the early stages of continued pre-training, we tested the performance of various JAM models. Our main goal was to maintain the performance of the parent models after merging them. Combining image and text processing in one model is challenging, so we wanted to measure how well our different JAM models retained the original performance compared to the two parent models that specialize in individual modalities. For the text modality, we compared the zero-shot performance on common-sense reasoning tasks like PIQA, Arc Challenge, Arc Easy, Story Close, Winograd, and Winagrande. We also reported some influential language learning models and our model fine-tuned with a 4K context as a reference. The JAM uniform model performed slightly better than the JAM width model in text-only tasks. However, it's important to note that this approach combines the functions of both parent models within a limited 7 billion parameter space. Our results show that the knowledge from the parent models can be mostly recovered using only a small portion of the original pre-training data. The JAM cross model performed the best, highlighting the strength of our bidirectional cross-attention mechanism. To evaluate the performance of our models in the image-text modality, we compared them using the validation perplexity on the MS-COCO dataset. We believe this metric strongly correlates with performance on subsequent tasks like image generation and captioning. Unlike the text-only tasks, the JAM width model performed better than the JAM uniform model in the image-text tasks. The JAM width model was particularly effective in maintaining image-text performance relative to text-only performance. Despite a drop in performance, the JAM uniform model still offers a good balance between parameters and performance. Interestingly, our JAM cross model not only performed the best among the JAM models but also outperformed our foundational image-text model, CM3 Leon. We think this improvement is due to the integration of new textual capabilities and an increased parameter count inherent to the combined architecture. Our instruct-tuned JAM cross model produced high-quality image-text outputs. To show its ability to generate coherent responses that interleave different modalities, we provided a large set of generated samples. The samples generated with retrieval were obtained from the model Instruct tuned with a mix of pre-training image text Shutterstock data and our Instruct tuning datasets. The samples generated without retrieval were obtained from the model Instruct tuned only on our Instruct tuning set. The generated samples show a coherent integration of image and text, demonstrating unprecedented abilities at this new task. Overall, we found our retrieval-augmented solution to be more effective than standard image sampling, improving image quality. We also compared our model with the most relevant previous work, GIL, that features mixed-modal generation. We used our retrieval-augmented JAM cross-model and sourced generations for the GIL model from the original paper. From this comparison, it's clear that our model produces better overall responses. The generated text is more complete and exhaustive, and the generated images are more relevant to the text context. We note that our method is the first capable of such coherent and interleaved generation with a focus on instruction tuning. Our fine-tuning procedure effectively learns the style of the dataset, not only for text but also for images. Our model opens up the possibility of wider adoption of mixed-modal generation in real-world applications. Section Summary. The authors use a mixture of publicly available text data, including English Common Crawl, C4, Wikipedia, Books 3 from the Pile, and Archive, to train their language model. They also collect an image text dataset from WikiHow, ensuring diversity by sampling balanced articles from each category with high community ratings. The authors evaluate the performance of their jointly autoregressive models, JAM, in both text and image text modalities, comparing them to parent models specialized in individual modalities. The JAM cross model performs the best, demonstrating the strength of their bidirectional cross-attention mechanism. The authors also show that their retrieval-augmented JAM cross model generates high-quality, coherent, and interleaved image text responses, outperforming previous mixed-modal generation models. Section 3.3 Ablation Study. In this section, we'll discuss an analysis we conducted to compare two methods for the width concatenation model, duplicating the original model's weight or using the average to initialize new parameters. Our findings, as shown in the table, reveal that duplicating the weights is more effective than averaging them in maintaining the original model's capabilities. We also conducted an analysis on the cross-attention model, as shown in another table. We examined the frequency of inserting cross-attention layers and the effect of not using any cross-attention layers at all. These tests were carried out with a training set of 25 billion tokens, keeping all other parameters consistent with those reported in section. It's important to note that this is a shorter training setting compared to our total training of 50 billion tokens, and the performance difference increases as training continues. We further analyzed the contribution of image text pre-training data in the instruction tuning process. The results, presented in another table, highlight the importance of using pre-training data in the instruction tuning process to maintain the MS-COCO PPL. We didn't report WikiHow PPL because our analysis of the models showed that it doesn't correlate with generation quality in the same way. Moving on to generative text-to-image models, this field has recently been dominated by diffusion models. Recent improvements have utilized pre-trained text representations like CLIP to enhance the quality of generation. Alongside the development of diffusion-based generative models, significant progress has been made by autoregressive token models. These models encode images into a discrete latent space and can be processed as a standard sequence-to-sequence modeling task, allowing for the application of techniques used in large language models. A key factor that has proven beneficial in enhancing text-to-image generative models is retrieval augmentation. This approach involves prefixing decoder-only models with retrieved images during training, resulting in a significant efficiency boost for the training process. This strategy has been scaled to achieve state-of-the-art performance in image generation using 5 times less training compute. In our work, we adopt their model as our text-to-image autoregressive backbone. In the field of multimodal language models, there has been considerable recent development. Several previous studies have focused on connecting language models to visual encoders. These methods typically train a network to map between a pre-trained image encoder and a language model. Flamingo introduces cross-attention into a frozen LLM to inject visual features and trains a large corpus of image text pairs. In our work, we also use cross-attention to bridge the two models, but our mechanism is bidirectional between the vision and language models, unlike Flamingo, where the visual knowledge is injected into the language model and not the other way around. Instruction tuning aims to teach language models to follow natural language instructions. Various methods have been proposed for instruction tuning, using existing NLP datasets converted into instruction formats, or using LLMs like GPT-4 to generate instruction data with better diversity. Recently, Lima demonstrated that 1,000 carefully curated samples are enough to achieve competitive results compared to larger instruction tuning datasets. The authors hypothesize that most of the knowledge is learned during the pre-training, and the instruction tuning teaches the style to interact with the users. In our work, we explore using a small set of multimodal instruction tuning data to fine-tune our model, verifying the effectiveness of a small dataset in this multimodal setting tailored to image generation. Unlike previous works, we explore instruction tuning-focused mixed-modal generation, paving the way for more significant adaptation of multimodal models that can generate interleaved image-text output.